convert potassium cation into potassium metal. We don't have a reaction in our body. So for the Nernst equation, for physiology, I would ignore this. I'd move this over 3 spaces because I'm worried about millivolts. And you might have seen something like this for physio. How many of you have seen around -60 log of like out over in terms of millivolts? Does that sound at all familiar? Does this look vaguely familiar to you where it comes from, or at all from something you've seen in probably neuro? Eek? Is that an eek yes or an eek no, or is that an eek profanity spelled in a way I don't recognize? Okay. So does anybody remember this from like action potentials, that this is the voltage, the threshold voltage or something when you can get a neuron to fire? Does that sound familiar? Because I'm fishing for you guys to teach me bio as opposed to the other way around. Okay, so the 60 millivolt is a threshold, and oh yeah, 70 might be the numerical value that they taught you as a threshold. This is for the calculation part, and this comes from 0.059. Temperature's a little bit higher, so it's at 60 or 61. So the equation should be 60 to 61, but you want this voltage to be 70, roughly you're saying, and this is around 60, which means this has to be log of about 11. So you keep on pumping, pumping, pumping until this is maybe 11:1 ratio, and then that's enough voltage to bam, fire off. So when you keep on pumping it out and you get the imbalance, it discharges. So the 70 you're talking about that's what you're targeting. That's the number you're trying to get at. This is the calculation to figure out what the concentration is that makes that happen. So this equation is the physio form. The one before I erased it is the so-called GChem form. And I just want you to recognize that I don't care about concentrations because that's a millivolt term. In GChem, I only care about the E naught. I don't care about E naught in physio because there is no chemical reaction. It's just purely charge distribution. So I hope this is helpful. The lack of feedback in the chat box makes me a little worried, because if this is something you haven't seen before, then Spencer will cover it in neuro. But I think, and I'm thinking secondhand, I never actually took a physio class, so keep in mind I'm doing it, I guess, vicariously through previous students. I thought that was, or some variation of this was something that was pushed on most everybody in a neuro class, or the neuro portion of a physio class. So for action potentials. Yeah, I know. So you guys are burnt. I'm going to power through only because this is like something people are going to look at later. But if you guys are just spent and burnt, revisit it. I mean, and that's the thing. I realize you guys are just so overwhelmed with just the overload week. And physio, okay, yeah, and it's fine. Again, I'm going to count then on Spencer to bring that up because I don't have the expertise to bring it up. But that is an equation that you might have seen as sodium plus over potassium, or sodium out over sodium in, or some variation on what the professor might have done. But know that it's the so-called Nernst equation. Okay, I'm going to push through this. I'm going to erase what I have here, get rid of the physio portion, and focus just on GChem. 3, 2, 1. Oh, okay, so some of you, like little pieces you remember. So you remember the sodium-potassium distribution. So my putting out and in didn't really help you at all. If I would have put sodium specifically concentration or potassium, that would have been more recognizable. My fault on that one. Okay. Yeah, I was being so utterly lazy by talking about like sodium concentration outside compared to inside. I could have done potassium inside or potassium outside, or sodium to potassium ratio. Then it would have looked familiar. Okay, my apologies on that one. I was just being lazy on what Q is. But Q is just a ratio of one side to the other. Reactant to product, outside to inside in the cell, whatever they're talking about. Okay. The key thing, over time, reactants go down, products go up, so Q gets bigger. If this gets bigger and bigger and bigger, you subtract bigger and bigger number, eventually gets to 0. When this is 0, your cell has reached its dead end. So let's consider palladium nickel. I just want to do something different than copper silver. I'm going to just tell you that the overall voltage is 1.22, but if you want to look it up, palladium is 0.99, nickel is negative 0.3 or 23, but you reversed it. So this E naught came from the table. I'm just plugging it in blindly. But again, go back to the table and double check if you wish. 2 electrons because palladium is 2 plus, nickel is 2 plus. So 2 electrons are transferred from nickel to palladium when it gets reduced, when palladium gets reduced. So you divide by the number of electrons 2. This is your standard conversion factor. Honestly, it's more of a memorized number than anything else, but 0.06 divided by 2 is 0.03. So here's what I want to plug in. I want to see how important this number is compared to this number. I'm going to give you 2 mathematical scenarios. A case where you have 10 times as much product as reactant or 10 times as much reactant as product. I'm going to look at both of these. So in the first case, when reactant is 10 times product, so big denominator, small numerator, it's log of 1 over 10. Log of 1 over 10 is log of 10 to the minus 1. I want to just revisit this for a second. Log of 10 to the x. Don't fight the power, just bring it down. So log of 10 to the minus 1 would simply be minus 1. So minus 1 times a minus here is minus means plus. So how many agree 0.03, this calculated term right here, was significant or insignificant compared to 1.22? Insignificant. Perfect. It's just a little bit more. Equally, if it's now 10 over 1, I'm going to say mostly products, 10 over 1, log of 10 over 1 is log of 10. That's 1, so it's minus. So basically, here's what we're seeing. We're seeing that this number, 1.22 plus a little, and 1.22 minus a little goes to here. How many would definitely agree this is what you experience with your electronic equipment? Do they run at pretty much constant voltage, constant everything, everything's fine? Until, how many have seen that little 20% left, do you want to do something about it? 10% left, you want to do something about it? 8% left, screw you, we're doing something about it. So is that the way things basically run? It suddenly shuts off because of this part suddenly becoming significant. But voltage stays relatively constant. Okay, the one thing I want to do, we haven't covered it yet, but titration curves look like this. How many learned that this is where pH equals pKa, and that it is essentially pH equals pKa plus log of AHA? I need to write that in a different spot. I'm now squeezing room and I apologize. Let me choose a different color as well. AHA. I'm not even going to bother putting signs or concentration on it because I don't have space. But does that equation look somewhat familiar? pH and E, pK a constant for the thing and E a constant, log of product over reactant, except there's some value. Okay, so real quickly, so I know that older devices, calculators, sometimes numbers get hazy. Yeah, that actually is more the fact that it's a very, very slight decrease. And there is some threshold where they need a certain amount of current to make the polarizer turn on and off. And when you go past it, suddenly the device can't run on that voltage. So it's also sensitivity to the voltage. So it's not so much a battery phenomenon as the thing running on the battery. So, and yeah, the fact that these are very similar, and is the graph looking very similar? Is this part of the graph looking an awful lot like this part of the graph? So if they asked you, what is the voltage right here? What would you say? This is so cool, you guys. I feel a second wind coming on. Perfect, exactly, 1.22. 1.25, 1.19, but 1.22. Perfect. And that's a circle. I should color it in. That is not a zero. Beautiful. Feeling pretty good about this. Okay, one quick question. And I know I had promised I'd do questions at the end and a totally separate one, but I ended up, because of all the other embedded questions fit within the context, this would have been the one at the end. So, give you a minute, talk in a minute. Thank you guys for being such good sports. And I realize I'm trying to figure out how I've gone so far over time. I think trying to mop up some of yesterday's stuff, which I should have just let it go. I'm worried about that for a different time. For this one, the words I need to know. You need to have a good vocab. What is a galvanic cell? Oh no, I must be using the wrong pen. Oh, okay. What is a galvanic cell? Favorable or unfavorable? Favorable, perfect, which means E is negative or positive? E must be positive, delta G negative. Perfect, got it. Okay, copper is being reduced, which means the other compound must be getting oxidized. So what I'm looking at is the following. Copper is getting reduced, which I know is a 0.34. So the other reaction, so for copper getting this, it's 0.34, the metal going this way. Tell me intuitively what you think. Which do you think is a more expensive metal, copper or palladium? I want you to do this intuitively before we actually do it calculation-wise. Palladium's more expensive. Would it make sense, if palladium is so expensive, that palladium would want to rust away while copper plates out? Would that be economically feasible? No. So intuitively, you should get rid of that. If it's something like palladium, platinum, gold, silver, precious metals, they probably want to be reduced more, so copper wouldn't get reduced, the other metal would. Number-wise, I plug in, it's a positive 0.99 here, but it has to be negative for when it's reversed. So palladium would be negative 0.99. Sure enough, negative. Palladium does not work. Does that surprise you? Hopefully not. Are you allowed to do that? Are you allowed to use real-life experience and common sense to help answer questions on the MCAT? You have to. You must. Trust. Yeah, zero shame. No pride. Whatever I get a right answer, I don't care. I'm going to doctor school. Okay. Nickel is in both answers. So the fact that I'm doing nickel here and plugging it in, good call or bad call as far as time efficiency on the test? Bad call. Didn't need to do it. So that one is bad call. I just need to look at zinc. Zinc we've seen a few times, so I'm going to power click it. But zinc, I know when I reverse it, it's 0.76. Positive 0.34 added to a positive 0.76 is 1.10. That'll work. No surprise. Best answer. C is in cool, but man, that was a lot of work. Okay. Last two things I'm going to turbo through just to present definitions. And don't overthink it, but it is terminology you need to know. So two things. Number one, electrolysis. So electrolysis, what does this word mean if I break it in two parts? Electro and lysis. What does lysis mean? To break. Electro, I'm using electron flow. If I put two electrodes into a tank of water, adding salt, it'll help it happen, but just put it in here. If I put enough voltage, I can get water to split apart into hydrogen gas and O2 gas. Would this be pretty good if my goal was to generate pure H2 or pure O2 gas for some reason? Would this be a pretty good purification technique? Or if I wanted to have a hydrogen-based car, but I didn't want to carry around a big tank of hydrogen because my good friend who built the Hindenburg gave me a hint, really don't want to carry around a lot of hydrogen in a tank, especially in something that can be hit and struck on a freeway. So could I make hydrogen on demand using a hydrogen fuel cell, which is basically electrolysis? You bet. Little Orphan Annie, fat cat, anode, cathode, fat cat here, so cathode, anode. Got to label everything. Got to be able to recognize that. That's always a starting point. Is H getting reduced or oxidized in this process? A couple ways you can solve it. Is H, from hydrogen's perspective, is it gaining or losing oxygen when it goes from H2O to H2? Losing O, loss of O is oxidation or reduction. So gaining O, oxidation, but this one's losing O, so losing O would make it reduction. Perfect. It's also going from +1 to 0, reducing its charge. So H2 is getting reduced. O2 is losing hydrogen. It's also going from -2 to 0, so it's being oxidized. And you know what? It takes time. You got to say it to yourself over and over and over, and it's still such a pain. And it will happen. It will come with enough practice. But the thing is, it's one of those things because it's just the wording of it just doesn't seem right. And so it just takes a while to beat it into you. That's a good thing. As a teacher, I'm telling you, do something until it gets beaten into you. Good strategy, but it works. Okay, for this one, the cathode would be the site of, I forget, oxidation reduction. What color is Leo? What kind of animal is Leo? Leo is a red cat. So reduction, H is reduction, cathode. So at this cathode, I'm going to get H2 forming. The anode, oxygen is getting oxidized, so anode here. Over time, I will build up H2 bubbles. O2 bubbles, if I collect them up here, I can get purified gases. So electrolysis is for purifying materials. I'm showing gases, but we can also do liquid. We can also do metals. We do it in a molten salt. The presence of water means water is going to reduce, but if you put other things in there, they can potentially. Generally speaking, do you do the easiest thing or hardest thing? You personally. Two choices. Take the hard route or the easy route. What do we choose? Easy. Chemistry. For chemicals, they have two reactions. Do they choose the easier one or the harder one to do initially? Easy one. You take your easiest, most acidic proton first. You reduce the easiest material in solution first. You always. So if there were other things in here, the one with the easiest or best reduction potential gets reduced. The one with the easiest or best oxidation potential will get oxidized. I've only shown H2 and O2 because I've only had water. So if I do this with distilled water, but if I have other ions that could potentially be reactive, easy is good. Easiest one first. Last thing, and I swear this is the last thing. You have your fancy rims on your car. Unfortunately, you drive around in the rain. And if you live in an area that has salt on the roads, because they melt the snow, you have salt water on the roads, which when coupled with air, will start ruining your car, including your rims. So can you do something to protect it? You could move to Mars where there's no rain, no oxygen, your car will last longer. Downside, you'll die in a few seconds. But I mean, your car will look good. Because we live here on an oxygen-rich planet, we have to live with oxygen. So instead of trying to avoid oxygen, can I instead put out a sacrificial lamb? So if my rims are made out of iron, if my car frame is made out of iron, if my body is made out of iron, my car body, I should say, then iron can be oxidized. It's favorable to oxidize in air. So can I galvanize by adding a sacrificial metal? So sacrificial implies it should be more reactive or less reactive than iron. What's your intuition tell you? More reactive. Okay. Next question. You want it to be a lot more reactive than iron or just enough? In chemistry, our motto, barely get by, just enough. So I want something slightly more reactive than this. So if I chose nickel, is nickel a good call? Yes or no? Nope, it's not reactive enough. Iron is more reactive. Put nickel on iron, iron's still going to get oxidized. What about sodium? If I put sodium, so I'm going to say put a whole bunch of sodium on your car and then go driving in the rain. What do you mean too much, Brooke? Why? What's going to happen? Fire. It'll be a big fireball. Probably not the best plan. A little too reactive. So I think it sounds like a fairy tale. First one was not reactive enough. This one's too reactive. I need one that's just right. Typically, there's a couple metals that could do it, but we use zinc because zinc is cheap. Zinc is one we can do this. So a really cool proof in the pudding of this. How many have ever had your tires changed on your car? One person. Two. Okay, perfect. Then you're our guest of honor here. Did they charge you for something called weighting and balancing? They spin the tire to make sure it rolls correctly. Because the valve stem is on there, do you agree that's one side of your tire is slightly heavier than the other if you divide it into halves? So what they do on your rim, you ever see those little pieces of metal that they clip to the rim opposite of your valve stem? And maybe you've ever seen that on your rim, if your valve stem of your tire is here, oh shoot, I was supposed to do that in a different color. So here's your tire. How many of you ever noticed they put a little piece right there. Twofold. One, to offset here so it rolls evenly, like a centrifuge. You always put something on the opposite side of the centrifuge so it spins in balance. But number two, they make it out of zinc. Why do they make it out of zinc? Said the galvanizing fan. Exactly. So your rims don't oxidize away. So they weight it for a physics phenomenon, but they use zinc so that it helps protect your rims, make them last longer. So they used to put a lead weight on there, toxic and I don't know, just weird. Now they put zinc. So hopefully it seems okay. Also, newer pennies stain shinier because the inside it's now copper plated zinc. You can tell the difference between like an 81 penny and earlier and 82 and later when they started putting zinc in the middle. So our pennies stay much shinier nowadays than they used to. Leading to, see, I don't know if you guys can hear it. I'm going to pull this. Are you hearing the nightclub disco music to your copper chain? All righty. I need to let me get out of this. So. Oh no, it won't escape. No, the disco music won't end. Okay, I unfortunately lost my chat box in doing this. Oh, chat box back up. Back up. Again, thank you guys so much for being so patient through a long lecture that went longer. So yeah, I know everybody's back because of disco music. It's like now you're all awake. Sorry, oh, what was that? Like the alarm clock music? But hopefully this seems okay and puts it into perspective. And if Fridays work out, next one will be a little bit shorter than this. I know disco music is going to be the saving grace to keep everybody like motivated or angry. Either one, you're awake. Yeah, my goal is to have these help. I'm going to plug back in so that I sound a little bit cleaner. Yeah, and if you look at it that way, you don't have to read the books. You can come to the lecture a little bit more prepared. Yeah, I think because I've already put it out as 1 to 3 and people are sort of locked into it. Is it a bad time? Did I pick an off time? Although, you know what? Actually, we're the group that's doing it. So the people who are here, obviously this worked, but okay, good time. Yeah, I think we hit a number right around there. Okay, I'll probably just keep it at this time too then. Yeah, I know it goes right through the middle of your prime dinner time. And so sorry about that. And then also it screws people on the West Coast who work full time out of it. So yeah, but thanks to the kindness of Jonathan, people who do get screwed out of time can always come back and pick up part of it. And I will generally go a little bit slower because I'm assuming people are going to watch this and can always, it's easier to hit fast speed to go through things than it is to go slow speed and rewind. Right as I said that. So yeah, for some things go half speed, some things go full speed, some things go double speed. But I think, yeah, you can go faster at 2 times speed, especially when you know it. But anyway, and then again, I don't anticipate trying to mop up stuff that just happened. I anticipate trying to preemptively get ready for a different lecture. So next week, hopefully, it'll be a little bit better. So a couple of things just want to go over, and I really want to go over that equilibrium thing because as I was watching the chat box and everybody was saying, no, this is what it is. It just, I'm like, oh, come on, just admit it is what it is and move on. And it just didn't happen. So anyway, so I'm probably going to sign off at this point just because I've created a quiet house. Oh, the survey, anytime, basically, it's just, it's going to all be summed together and it's going to lead to the decision of basically Josh wants to know if he should keep doing it or not keep doing it. And that feedback, just getting somebody to step in or not is the thing. Not physio. Physio is going to be Spencer. Spencer is friggin' awesome. Prachi is going to keep doing genetics. Prachi is awesome. They are friggin' awesome. Unfortunately, Spencer is gearing up to head off to medical school. Prachi is at medical school. So, I mean, they're both, oh no, actually, no, she's gearing up to go off too. I'm off on that. Yeah. Oh, you're welcome. Yeah. Although, and this is something that if somebody can tell me what the heck happened, I just know somebody's talking about 5 bonds of carbon being an issue. So could you screenshot that, what the heck they're talking about? But they were saying it wasn't just the result of fast drying, it was just the way everything. 5 bonds, but also, from what I understand, it was an aldehyde CHO at carbon 1. It was a ketone with 5 bonds of carbon at carbon 2, and the phosphate was on 5. From what I understand, it was just butchered every possible way you could butcher it. But I don't know exactly what they're saying. And in talking with him, like, hey, you might want to keep an eye on that. It just basically was saying, well, it's just one thing. So I just want to be on the right page, because there is a chance he could salvage it. Okay. Okay, yeah, you can find, I just don't know where to fish, but I appreciate that. And it could be a positive thing. And feedback can lead to a positive change. It really can. So we'll see how that all works out. And this is the hope. Well, thank you. And again, thank you guys for the positivity and the good everything you guys give off. Okay. I will look for the ping. Oh, and for attachments like that, probably better to email, because again, I use a different computer that has absolutely no email that I can access on it. So kind of lame, but yeah, it's the Discord only computer, so to speak. Thank you so much. All right. Well, I'm probably gonna log out of this, stop my sharing. And once again, hey, one thing, if you wouldn't mind just give me a heads up saying, hey, we're done, the recording is done, because then I can start swearing like a truck driver again. Oh.